Welcome viewers to the third segment of the third lecture for the online series of lectures for the course of Algebraic Topology 1. We are going to start this segment with the definition of local homeomorphism. The map P from E to B is called a local homeomorphism if each point small a of big E of this topological space E has a neighborhood that is an open subset U of this topological space E containing E that is mapped homeomorphically by P onto an open subset of the topological space B. Okay. Alright. Now let P from E to B be a covering map and E is an element of the topological space E. Also let P of that point E is equal to X in the topological space B. Since P is a covering map, there exists U contained in B open containing the point X that is evenly covered by P. In other words, we should be able to write P inverse U as a disjoint union of open sets V alpha as alpha runs through the index set J. Okay, where each V alpha is open in E. Okay, now X, which is equal to P of E, is contained in U, right? X is contained in U, so that E is contained in the pre-image of U under P. Therefore, E is contained in the disjoint union of these open sets, V alphas, right? So that E is in V alpha for some alpha in the index set J. Alright, so now from the definition of covering map, we know that P restricted to each V alpha, which is a map from V alpha to the open set U, is a homeomorphism, okay, which follows from the definition of a covering map. Therefore, given E in the topological space E, we have found an open set V alpha contained in E containing the point E so that V alpha gets homeomorphically mapped to the open set U of P. Therefore, P is a local homeomorphism. Okay, so we have thus seen that if P from the topological space E to the topological space B is a covering map, then P is a local homeomorphism. The converse of this statement is not true in general. The converse of this statement is not true in general. As the following example suggests. Okay, so here is an example that shows that a local homeomorphism may fail to be a covering map. Okay, example 3. It's a variant of the previous example where the form of the function stays the same, but the domain changes. the domain of the function, the map changes. We denote by p twiddle the map from the positive real numbers to the unit circle given by the same function p twiddle of x to be equal to cosine of 2 pi x comma sine of 2 pi x. Okay, this map is surjective and it is a local homeomorphism. We have seen before that there is an open cover of S1. Open cover, by open cover I mean a collection of open subsets of S1, the unit circle with, we have seen these facts earlier, the inverse image of U1. So there are four open sets here, U1, U2, U3, U and U4 of S1, and we have seen that the inverse image, so P stands for the previous map that we had earlier, okay, from R to S1, given by P of x is cosine 2 pi x sine 2 pi x. So the expression for P and P twiddle are the same. The only difference between them are the underlying domains. Okay. For one, the domain is the whole set of real numbers, and for the other, it's just the positive reals. Okay. So we have seen earlier that the inverse image of U1 under P was this disjoint union, the open set from n minus 1 quarter to n plus 1 quarter. Okay, and the inverse image of U2 being equal to the disjoint union of the open intervals of the form n to n plus 1 half. Then we have this inverse image of U3 under P to be equal to the disjoint union of intervals of the form n plus 1 quarter to n plus 3 quarter. And finally we had the P inverse U4 to be equal to the disjoint union of open intervals from n plus 1 half to n plus 1. Okay, for this covering that. Okay, from R to S1 given by P of x is equal to cosine 2 pi of x, 2 pi x sine 2 pi x. Okay, we have seen that this is a covering map before. Okay, and now we can easily compute the inverse image of U1 under the inverse images of U1 under this new map in the following way. Okay, let me erase. So the inverse image of U1 under P twiddle is just the inverse image of U1 intersected with the positive reals. Okay, that will give us the inverse image of U1 under P twiddle, and that is just you know, the 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 n equal to 0, the v0 thing gets shortened, and that is just 0 to 1/4, and it gets and the disjoint union of this interval with these disjoint unions and belonging to the set of positive integers n minus 1/4 to n plus 1/4. This, okay, and this we are defining this guy to be equal to the disjoint union of n belonging to this set z plus union 0 over v and twiddle. Okay, all right, so here by z plus I mean the strictly positive integers starting from 1 to all the way up to infinity, and by r plus I mean the real numbers that are strictly positive. Okay, and now you see that according to the definition of the v twiddles, v v sub 0 twiddle is just 0 to 1/4, and v twiddle n is equal to n minus 1/4 to n plus 1/4 for n belonging to the set of strictly positive integers. Okay, good. This is v twiddle n. All right, so this is the way we obtain the inverse image of u1 under p twiddle. Okay, similarly, let us find the inverse image of u2 under p twiddle, which is nothing but the inverse image of u1 under p intersected with the positive reals, which again is the disjoint union of the open intervals of the form from n to n plus 1/2. Here n belongs to the set of strictly positive integers union this singleton 0. Right? This is, so we now define this new open set Vn prime twiddle. Okay, similarly p twiddle inverse u3 is equal to p inverse u3 intersected with r plus disjoint union from n plus 1/4 to n plus 3/4, and we define this open sets by, we denote these open sets V and twiddle triple prime, right? And it is easy to see that R plus can be written as the union of all these sets, V and twiddle, and belonging to Z plus union the singleton 0. Sorry, this is union, not disjoint, because there are overlap between two such sets. And belonging to Z plus union singleton 0, V and twiddle prime union, and belonging to Z plus union singleton 0, V and twiddle double prime union and belonging to Z plus union singleton 0, V and twiddle triple prime. One can easily check that R plus is a union of all these sets. Okay, good. Let me erase this top part. Now let me draw a picture quickly. The diagram gives us the same open arc that we discussed before in the last segment, which is the arc U1. This bold part of the circle is the arc U1, open arc U1, and we denote another sub-arc of this arc denoted by B, and there is this point 1, 0, okay, and the origin being 0, 0. Okay, so the arc U1 in particular a neighborhood containing 1, 0 is not evenly covered by P twiddle. Okay, so U1 is an arc containing the point 1, 0. There can be other arcs which also contain 1, 0. Okay, so it holds for any arc or any neighborhood, any open arc containing 1, 0. The problem lies with the point 1, 0. Let's see how it happens. The arc U1 is not evenly covered by P twiddle, since for the I'm putting it within the quotation slice because it is not a slice in the ordinary sense, the way we defined it for a covering map. Okay, it fails to achieve some important property that it should have it did for a covering map. Okay, that's why I'm putting it inside the quotation mark, still calling it slice. Okay, so the arc U1 is not evenly covered by P twiddle, since for the slice V0 twiddle which is 0 to 1 quarter. Okay, remember that we defined this uh, um, Bn twiddle. We also defined Vn twiddle prime, Vn twiddle double prime, and Vn twiddle triple prime. Okay, so here when n is 0 in this case. Okay, so this slice V0, V twiddle 0, or V sub 0 twiddle from 0 to 1 quarter, for this P twiddle restricted to V sub 0 twiddle, which is a map from V sub 0 twiddle to the open arc U1, is just an embedding. It fails to be a homeomorphism. Embedding. So um, you learn about embedding in while you do points at topology. Okay, embedding means that that you know uh, the map is injective, but it's not surjective. But the image of V sub 0 twiddle under this embedding map is a subset here. Okay, so it is an embedding. It by embedding it means that this P twiddle restricted to this V sub 0 twiddle from V sub 0 twiddle to the image of this guy. V P twiddle restricted to V sub 0 twiddle of V sub 0 twiddle. This guy is a homeomorphism. So in some sense, if you extract the image part, extract out the image part from the whole codomain, then you get a homeomorphism. Okay, so it's an injective map. The embedding means that it's an injective map, but from the domain to the image, it's a homeomorphism. Okay, all right. So one sees that it's just an embedding. It fails to be a homeomorphism for this open set of R. Therefore, okay, so I forgot to write it. I should have written it that P, this map, the restriction from the sub 0 twiddle to U1 is just an embedding, not a homeomorphism. Okay. In fact, P twiddle restricted to V sub 0 twiddle from V sub 0 twiddle to the image of this map, V twiddle restricted to V sub 0 twiddle B sub-0 twiddle being a subset of U1 is indeed a homeomorphism. That is actually the definition of embedding, right? Homeomorphism. Therefore, B twiddle is not a covering map. Okay? It's not a covering map. Okay. Now, any neighborhood of a point, any neighborhood, any neighborhood of a point in R plus will be contained in one of the open sets Vn twiddle, Vn twiddle prime, Vn twiddle double prime, Vn twiddle triple prime for some n belonging to the set of positive integers, strictly positive integers, union the singleton 0. Okay. Because we have written down R plus as a union of all these sets for all n belonging to these sets. All right. Let x0 be a point in R plus, okay, and W is a subset of Vn twiddle double prime, for example. Okay, it can be anywhere else, but just choosing, for example, to be V twiddle sub n double prime. Okay, with x0 belonging to W, right? And P twiddle, right? P twiddle restricted to W is a map from W to, right, P twiddle of W, which is a subset of U3, okay, is indeed a homeomorphism. Is indeed a homeomorphism. Okay, it happens for it. So if for any, so it can be any. So it happens for any of these choices. Okay, one can check that it happens for any of these choices. So if you take the the W in those choices, if you take W to be a subset in one of those choices, then the map, the restriction map from W to its image is going to be a homeomorphism. Okay. Therefore, although P twiddle is not a covering map, it is a local homeomorphism. So let me go back and draw the picture, draw the diagram of the circle. Remember that I said that you have this open arc U1. So let us take a smaller sub-arc of U1 containing the point 1, 0, okay? And here is this the real line. So the positive real line starts at 0, okay? And here is so say that this is 1. So the 1/4 is here. So this is 1/4. So now you cannot show that this interval is homeomorphic to this neighborhood containing the point 1, 0. You can never show that. But you can always show that this guy is homeomorphic to an open subset of this set, which is like this. Okay? And this is precisely why this P twiddle is a local homeomorphism. This is what I am writing here, that P twiddle restricted to W, from W to the image, which is this thing. P twiddle restricted to W at W. Okay, is a homeomorphism. Okay, because the negative part that we had earlier for the definition of P, which included this negative 1/4 to 0 as well, right, including the point 0. That was from negative 1/4 to 1/4, right, which was precisely V sub 0, right? And that is homeomorphic to this open arc. That was homeomorphic to this open arc. We have shown it earlier. Now you are, taking a part of it away, and that is the reason it's no longer a homeomorphism, but it is homeomorphic to an open subset of the earlier set. Okay, good. So now an important fact: in example 3, we saw that the restriction of a covering map in general is not a covering map. Okay, we saw that this map from R to S1 given by Px equal to cosine 2 pi x, comma sine 2 pi x is a covering map of S1. Okay, but when we restricted this map to the positive real numbers, we found that it's no longer a covering map. Okay, it's 2 pi x. It's no longer a covering map. Now, the following theorem tells us when this will be the case, meaning when the restriction of a covering map will also be a covering map. Okay. Okay, let's see. Theorem 2. Let P from the topological space E to the topological space B be a covering map if B0 is a subspace of B, and if E0 equal to the inverse image of B0 under P, then the map P0 from E0 to B0 obtained by restricting P is a covering map. Okay, let's prove this theorem. Prove. Given this point B0 in this subspace B0. Okay, so this is the subspace of the topological space B, and we are choosing a point B0 in this subspace B0. Let U be an open set of B that is evenly covered by P. Okay. Why? Because this is a covering map, and I'm choosing B0 to be a point in B0, but since B0 is a subspace of B, B0 is contained here as well, right? And by the definition of covering map, there is an open set U of B that is evenly covered by P. Okay. Okay. I think I need B0. B0 is contained in this open set U. Okay. That is evenly covered by P. Let this guy, this family, is a partition of the inverse image of U into slices, right? That is, the inverse image of U is written as a disjoint union of these open subsets of U. Okay, alpha in J. We denote this by equation number 2. Okay, where of course each V alpha is open. Each V alpha is open in the topological space E. Okay. Now, remember that B0 is a subspace of B, and E is an and right. Okay, HV alpha. So now I need space. Okay, so B0 is a subspace of B, right? And U is open in B. Therefore, U intersected with B0 is open in B0 in subspace topology. Okay, that contains B0, right? Why? Because B0 is both contained in B0 and U. So B0 is contained in the intersection. Okay, so this line is important. Also, the sets V alpha intersected with E0 as alpha runs through this index set J are disjoint open sets. In E0, okay, because V alpha is open in E, and E0 is a subset of E. So V alpha intersected with E0 is an open set in E0 in subspace topology. And since for two different values of alpha, V alphas are disjoint. Therefore, for this family, if I choose a pair, they are going to be, they will be pairwise disjoint, right? So these are disjoint open sets in E0, again in subspace topology. Okay, so indeed, what I have said earlier, if I take a member from this family, V alpha intersected with E0, and I take another member which is V alpha prime intersected with E0, then by elementary set theory I can write it as V alpha intersected with V alpha prime intersected with E0. Okay, for this state, alpha alpha prime in the index set J, right? And since this is empty set, this guy is empty. Okay, good. Now also the inverse image of U intersected with B0 under P is going to be equal to, by elementary set theory, inverse image of U intersected with inverse image of B0. Okay. Now inverse image of U is the disjoint union of V alphas intersected with E0. We have chosen this subspace to be E0. Remember, we denoted this subspace with E0 in the statement of the theorem. And by set theory, by elementary set theory, again it can be written down as the disjoint union of V alpha intersected with E0. Okay. In addition, since it follows from the definition of the covering map that P restricted to V alpha from V alpha to U is a homeomorphism, right? Since P from E to B was a covering map, right? Therefore, the restriction of P to V alpha, which is a map from V alpha to U, is a homeomorphism. And hence, the restriction of a homeomorphism is also again a homeomorphism. So P restricted to V alpha intersected with U0 from V alpha intersected with U0 to U intersected with E0 is also a homeomorphism. Okay. Right? So this equality along with this fact tells us that P0 from E0 to B0 is a covering map, right? Covering map, right? Because in this case we have been able to show that for each point B0 of B0 we have found neighborhoods which are evenly covered by P0. What are those neighborhoods? U intersected with B0. Okay, where we wrote this guy P inverse U intersected with B0 as the disjoint union of slices alpha in J, V alpha intersected with E0. These are the slices. Okay, so that, well, it's just so the map restricted to these slices is a homeomorphism, which follows from here. Okay, so which proves that this guy is indeed a covering map. Okay, good. So we are done with lecture 3. So basic concepts related to covering maps are covered in this lecture. Okay, so in the lecture we'll work with we'll compute fundamental group of a circle. Okay, so we know this topological space S1. Okay, S1 is a topological space endowed with the subspace topology that it inherits from R2. So it's a topological space, and we want to compute its fundamental group. That we'll do in next lecture. Next lecture we'll do that. Thank you for attending the third segment of the third lecture.